Hello calculus fans. Today we look at section 7.2 from the Stewart textbook, and this section covers trigonometric integrals. In this section we are going to use trigonometric identities to integrate certain combinations of trig functions. But before we do this, let's just review a little from Calc 1. And think about some of these antiderivatives. So the antiderivative of sine is negative cosine, right? The antiderivative of cosine is sine. Because remember, whenever you take the antiderivative, you can always check it. If I take the derivative of this, I need to get back here, right? The derivative of sine u plus c is cosine of u, right? The derivative of negative cosine would be positive sine. And a couple other ones, we've got the antiderivative of secant squared u du is tangent of u plus c. For cosecant squared, it would be negative cotangent of u plus c. And for secant u tangent u, we've got secant u plus c. And for cosecant cotangent, it would be negative cosecant u plus c. So when it comes just to trig functions, we have the antiderivative for sine and cosine, but we don't have tangent, cotangent, secant, or cosecant listed. Now some of you may have seen this one. May have seen this sometimes in Calc 1. When you talk about u substitution, you'll see this one. But let's just take a look and see what we can do. So in order to integrate the tangent function, what we're going to have to do is rewrite it first in terms of sines and cosines. And tangent is equal to sine of x over cosine of x. And if we write it like this, then we can actually integrate the function by u substitution. So we could say, let's let u equal cosine of x. Then du would be negative sine of x dx. And we can then divide each side by a negative 1 and get negative du equals sine of x dx. And the sine of x dx we've got right here. Because remember, sine of x dx, like if you really wanted to, do you guys agree what we could do is we could write sine of x cosine of x dx. Isn't that just the same as 1 over cosine of x times sine of x dx? And then maybe it's a little easier to see that this sine of x dx here, it's here, but you can really see it if you set it off to the side there. So anyway, we can integrate this now. This is sine of x dx is just going to be negative du. So that this would be equal to negative, basically 1 over u du. And we know the antiderivative of this is going to be negative natural log of the absolute value of u plus c, which is equal to negative natural log of the absolute value of cosine of x plus c. And this is the answer you'll see a lot of times for if you have a table of integrals and you have a tangent of x. A lot of times you'll see this for the answer. But there's another answer you'll see sometimes. So sometimes people don't really like the negative out in front. So we can rewrite this. If you remember the rules of logarithms, so just a real quick review here. There are rules for logs. I guess it doesn't have to be natural log. I mean, it doesn't. It could be any base. I'm not sure why I use natural log. But remember, logarithms reduce mathematical operations to a simpler operation. So natural log of a times b, instead of multiplying, if you use logarithms, you can just add, right? It's natural log of a plus natural log of b. So instead of dividing, you could do a simpler operation of subtraction, natural log of a minus natural log of b. And instead of exponentiation, you can do multiplication, so the b can come down and be multiplied. So you get b times the natural log of a. Well, it's this last one that we're going to do right here. Think if the b were a -1. So you got a -1 here, right? Like the negative, you can think of this as -1, and then we can move this up. So we can rewrite this a little bit. So we could rewrite this as, you could say this is equal to the natural log of cosine of x to the -1 plus c. And that's equal to the natural log of 1 over the absolute value of cosine of x plus c. And that, of course, is equal to the natural log of the absolute value of 1 over the absolute value of cosine of x plus c, because 1 is the same as the absolute value of 1. And now that both of these are in the absolute value, we could write it as the natural log of the absolute value of 1 over cosine of x plus c. And 1 over cosine of x, well, isn't 1 over cosine of x just secant of x? So this is the other way that sometimes this antiderivative is written. Okay, so if you don't want to use the negative here, you can use a positive, but then other people say, well, I don't really like secant, I'd rather use cosine. So whichever way you like, there's an answer for you. So the antiderivative tangent of x is either this or this. They're both equivalent, and you can just pick your favorite one. Now, if you were going to find the antiderivative cosine of x, of cotangent of x, it's going to be very similar. Very similar to this, very similar technique, and you'll find that out. And we'll talk about that in a second here. So this one is, if you rewrite it in terms of sines and cosines, it's kind of straightforward. But the next one here for secant of x, I imagine it probably was a trial and error process that made this one work. But I'll just show you something that will work for it, and then we'll see what the antiderivative secant of x is. So for this one, we have to multiply by 1. Okay, so I'm gonna just write it like this. So I'm gonna write this as secant of x, and I'm gonna multiply by 1 in this form. Secant of x plus tangent of x over secant of x plus tangent of x dx. Okay, so we've got it's the same problem, we're just multiplying by 1. And you'll see why we're multiplying by this particular value of 1 in a second here. But if I were to multiply here, I could just distribute this through the numerator, right? So if you distribute it through the numerator, you'll get this is going to be equal to secant squared x plus secant x tangent x. Denominator would be secant x plus tangent x. And then if you think about this one, think if you let this be u and you took the derivative to find du, you see something that might happen here? Now again, this is something that probably just somebody through trial and error, just looking for a way to integrate this with some sort of u substitution. If you play around long enough, you'll be able to find some combination that maybe works, like this one. So once you set this up, then we can say, okay, let's let u equal secant x plus tangent x. Then du is going to be secant x tangent x plus secant squared x dx. Right, just taking the derivative of secant is secant tangent, derivative of tangent is secant squared, and then look at what we've got. Secant squared of x plus secant x tangent x dx. So we've got it right there. So if we do that, we can say, okay, so this is equal to 1 over u du. Right, and we've got something very similar to what we had before. The answer to this is the natural log of the absolute value of u plus c, which gives us natural log of secant x plus tangent x plus c. So this is the antiderivative of secant of x. All right, so now we can fill in some of these blanks here. So for tangent, we've got a couple things we could write. you could write natural log of the absolute value of secant of u plus c, or you could write minus natural log of the absolute value of cosine of u plus c. Now, if you do the same idea with cotangent, it works out nicely, so there's only one answer, because you get the natural log of sine of u plus c, and that one works out well, so you don't really need to change anything about it. Okay, then for secant, we just figured this one out. This is natural log secant u plus tangent of u plus c. And now this problem here is actually a homework problem. So I'll tell you a couple answers. I'll tell you what you'll probably get by looking at how we did this. I think you'll probably get this answer. Negative natural log of cosecant u plus cotangent u plus c. Another answer that this is the answer from the back of the book. It's natural log cosecant u minus cotangent u plus c. And they're both fine. It just kind of depends on how you set up your problem to make the u substitution work. Okay, so a couple of different answers there. If you ask Wolfram Alpha this question, Wolfram Alpha actually gives you this answer also. Okay, so the main part of this section is dealing with integrals that involve combinations of sines and cosines or tangents and secants. Now, of these two, the sines and cosines are the ones that you'll see the most. But there are some cases for each of these types. So let's take a look at these. So case 1. And this is case for integrals involving combinations of sines and cosines. So it's something that looks like this. Sine, so m and n are some integers, right? So some power of sine times some power of cosine, and you want to integrate. So case 1 deals with an odd power of sine x or cosine x. So when you have an odd power, what you want to do is strip off one factor of the odd term to serve as the du. Then we're going to use a trig identity. Sine squared plus cosine squared equals 1. We use this identity to express the remaining portion of the integrand as powers of strictly sine or cosine. So they'd be the other one here. This will make sense when we try one of these. Then use substitution with this to express the integrand as powers of u. Oh, u substitution, right? So, all right, so to get started here, these are both odd, right? It's sine to the 5th and cosine cubed, so they're both odd. So really we could pick either one. But example 3 and example 4 are going to make a point because they're the same question. Example 3 says strip off a cosine of x. Okay, so by example 3, what we're going to do is we're going to say, okay, this is equal to sine to the 5th of x times cosine squared of x times cosine of x dx. Right, so it says strip off one factor of the odd term. So we're going to strip off one of these to make it cosine of x. And that's going to be the du. So this is my du, which means my u has to be sine of x. So I want all of this to be sine of x. So I need to get rid of this cosine squared. I'm going to use this to do it. Because if this is true, then isn't it also true that cosine squared of x equals 1 minus sine squared of x? Right, if you just take this equation and solve it for cosine squared of x, you'll get 1 minus sine squared of x. So in other words, from that we could say cosine squared of x equals 1 minus sine squared of x. So over here I need to get rid of this cosine squared and replace it with 1 minus sine squared. Okay, so this is going to be sine to the 5th x times 1 minus sine squared of x times cosine x dx. All right, then one last thing we're going to do is just distribute this through. And that will give us the integral of sine to the 5th of x minus sine to the 7th of x times cosine of x dx. Okay, so remember this is going to be the du, right? We stripped off one factor of the odd term to serve as the du, so here's the du. So that means the u is going to be sine of x. Then the du is cosine of x dx. So we've got du is here, and now we can substitute. So we could say, okay, this is going to be u to the 5th minus u to the 7th du. And if we integrate this, we will get 1/6 u to the 6th minus 1/8 u to the 8th plus c. And then, of course, we have to put the u back in. So u is actually sine of x. So this is going to be 1/6 sine to the 6th of x minus 1/8 sine to the 8th of x plus c. So this is the answer that we get. Okay, so now the other example is the same question, but they want us to strip off the sine of x and just see what the difference is. See if we get the same answer, if it's more work, so we can compare the two. Okay, so let's try this one. We're going to strip off sine of x this time. So what we would say is okay, this is going to be equal to sine to the 4th of x times cosine cubed of x times sine of x dx. We can see these are the same, right? We just put this, stripped off the sine and put it over here, but these are all being multiplied together. So this is the same. So now this is going to be the du. So the u is going to have to be a cosine, right? And we don't have to worry about the negatives, but basically u will be a cosine, so then the du would be a sine. So that means I need to put all of these in terms of cosine. So this time I need to get rid of the sine to the 4th of x. Well, if we go back to what we had before, we know that sine squared of x plus cosine squared of x equals 1. So if I were to solve this for cosine of x, solve this for sine squared of x, so I can put all of this in terms of cosine, right? So if I solve this for sine squared of x, I just subtract cosine from each side. And that would give me that sine squared of x is equal to 1 minus cosine squared of x. So I'm going to replace this. I'm going to think of sine to the 4th of x. Okay, let's consider that. So sine to the 4th of x is really sine squared of x squared, right? So then I could put sine squared of x, which is this, and then square that. So this is going to be, whoops, that's not what I want. This is going to be 1 minus cosine squared of x squared, right? Because this is sine squared, and I'm squaring that because I've got sine to the 4th. So this is sine squared squared. Then we have to multiply by cosine cubed of x. So we get times cosine cubed of x times sine of x dx. And then we're going to have to square this. So when we square this, remember, we have to take two of these, line them up together, and multiply them together, like a FOIL method, right? You have to FOIL this. So what we'll get is 1 minus 2 cosine squared x plus cosine to the 4th x times all the rest of it, cosine cubed x times sine of x dx. Okay, and now what we can do is we can distribute this through here, right? Distribute it through here. We want to leave the sine x dx here by itself, but we want to take this cosine and distribute it through. All right, so this would be equal to cosine cubed x minus 2 times cosine to the 5th x plus cosine to the 7th x times sine of x dx. And now we are ready. Now we've got this in terms of cosine, and we've got sine over here. So we can do our u substitution now. So we can go, all right, so u equals cosine of x, du equals negative sine of x dx. but we don't have negative sine of x dx, we have sine of x dx. So I'm just going to multiply each side by a negative to get negative du equals sine of x dx, and then we've got exactly what we need. So we'll swap this out, we'll substitute, remember there's going to be a negative coming through, so we'll get equals negative, we'll get u cubed minus 2u to the 5th plus u to the 7th du. So we can integrate this, and we will get, maybe I just to make it easier, well, all right. I guess we can, I'll integrate it and do the negative at the same time. So this is going to be 1/4 u to the 4th, but then the negative comes through, right? So we get negative 1/4 u to the 4th. Then we got negative times negative, which gives us a positive. And this will be u to the 6th. Then we divide by 6, so we get 2/6, which gives us 1/3 u to the 6th. And then we'll have negative times positive, so it'll give us a negative 1/8 u to the 8th plus c. And this is just again from the power rule, right? So then we can substitute back. So u is the same as cosine of x, so we can substitute this back, and we will get negative 1/4 cosine of x, or cosine of x to the 4th, plus 1/3 cosine of x to the 6th minus 1/8 cosine of x to the 8th plus c. Now if you look back at our previous answer, this one looks a lot different. So they look a lot different, and that will happen sometimes in this section. So sometimes you're going to look in the back of the book to check your answer, and the answer will be a lot different. So what we should do, maybe try to compare these two answers. Right, so the first answer had a bunch of sines, or a couple sines. This one has 3 cosines. So what I'm going to do is I'm going to graph both of these on the graphing calculator and see what it looks like. So when you graph these, you get something like this. So this first one here was our first graph with the sines, and then this one is our second graph with the cosines. So if you remember, if you look back to the original question here, because this is it's an indefinite integral, there's an infinite number of solutions, but they're all related. They just have a different value for c, which just causes a shift. So you can see these are the same graph, just shifted. So sometimes it's going to happen. You're going to get answers that look completely different from the back of the book, but they could both be right. And if you were to actually plot them out, you'd see, oh, look at that. It's like the same graph, just with a vertical shift. I should mention also is for this particular one, I hit zoom trig to put it in the trig window, and it looks like nothing's there. But then I changed the y-axis. So the y-axis on this one is really small. So I went from negative 0.05 to positive 0.05 for the y-axis. So really these are like really, you can barely see them in the normal window. They just barely go up. So I had to kind of zoom in along the y-axis to be able to see these. Another thing to notice is that this second one here, when we stripped out the sine of x, was a lot more work, right? Because we had to deal with squaring this. So there's a little lesson to be learned here. All right, so let's see. So this question here is just talking about they're really the same graph, just with a vertical shift. But here's something. Example 3 was easier. So when sine and cosine both have odd powers, the thing to do is strip off a factor from the trig function with the lowest power. That would be the easiest way to do it. Okay, so that's how we did with the first one. So just if you have a choice, you can pick sine or cosine. Just strip off a factor from the trig function with the lowest power. So, all right, what about this next example, sine cubed of x dx? And when you look at this example, there's an odd power of sine, and there is no cosine. So this one's kind of It's already decided for us, right? We're going to have to strip off an odd power of sine. So this one, what we would do, we could write this like sine squared x times sine of x dx. Okay, so this is going to be our du, which means our u is going to have to be cosine. So we're going to have to rewrite this in terms of cosine. But we already know we're okay with that because that is equal to, sine squared is equal to 1 minus cosine squared, right? Times sine of x dx. And now we're ready to go. Now we can say, all right, let's let u equal cosine of x, and du will be negative sine of x dx. So then negative du is equal to sine of x dx. And sine of x dx is right here, so we can swap that out completely with negative du. So this will give us negative 1 minus u squared du. Okay, so if we integrate this, I guess what we could do, maybe I'll do this negative out front. If I distribute it through here, I'll get a negative 1 and a plus u squared. So maybe I'll just do that. You don't have to, but this way you don't have to deal with a negative, right? Negative coming through is going to make this a negative 1, so I just put it here. Negative times negative is positive u squared. Okay, so then we can integrate this, and we get 1/3 u cubed minus u plus c. Then we swap it back out for the cosine. We get 1/3 cosine cubed x minus cosine of x plus c. Okay, so it's another example. So we talked about some of these examples when sines or cosines were negative. But what about when they have even powers, like case 2? So case 2, both sine of x and cosine of x have even powers. So both of them are even. Well, when that happens, when they both have even powers, so this is case 2, we have a couple of trig identities to use here. And I'm going to write these down. You've probably seen them before. Maybe not have seen them a lot, but we'll use them quite a bit in Calc 2. And I'll tell you an easy way to remember them. Okay, so they're both very similar. So cosine squared x, there's an identity that says this is the same as 1 plus cosine of 2x over 2. So notice what's happening here. The argument doubled. It was x, now it's 2x. Okay, now this one is going to be very similar, but it's going to be a 1 minus cosine of 2x over 2. Okay, same thing. The argument went from x to 2x. So the thing that I think is easy to remember this by is think of it like this. Think about in your life. Let's say you're at work and all of a sudden there's a giant change coming through. Is everybody going to be like, yay, I love change. More change, please? Probably not, right? People generally don't like things to change. So think about this cosine team. They're like, well, we're going to have to change the argument to 2x. And people are upset, but like, but you're still going to use cosines. Like, okay, they're feeling positive because they're still at least using cosine, right? What about this team? We're changing x to 2x and we're not using sine anymore. They're like, wait a minute. We don't like change, right? They're feeling negative. So the sine gets the negative, right? Cosine is a positive. All right, I don't know. It's just a little memory hook. So maybe it'll work. So the way we use this, though, either of these, is when we have something like this. So we want to integrate cosine, and it's squared, right? It's not an odd power, so case 1, can't use that technique. It's an even power. So with an even power, we use this technique here. So the cosine squared, we're going to use this substitution. Remember, whatever this angle is, it's going to double. So if it's 2x, when we substitute, it's going to be 4x. Right? So this one's going to, we can rewrite this as 1 plus cosine of 4x, right? Of 4x over 2 dx. And now what we want to do is think about this. This is really just 1/2. You could think this is 1/2 times all of this. So I'm going to pull out the 1/2. So I'm going to write this as 1/2 times 1 plus cosine of 4x dx. Everybody okay with this? This 1/2? Because if I distribute it through, couldn't I just multiply the 1 across the numerator and then have the 2? If I think of this as being over 1, 2 times 1 would just be 2. So it's okay, we can pull this 1/2 out and we get this right here. And now these are ready to go. The antiderivative of 1 with respect to x is x. The antiderivative cosine of 4x. Maybe by now you've done enough u substitutions where you can kind of see what's going to happen here without doing the u substitution. Just in case we'll do it. But basically, when we integrate cosine of 4x, so we'll do this one over here in red. So when you had this problem, when you first used u substitution in Calc 1, you'd say, all right, I'm going to let u be 4x, then du is going to be 4 dx, and 1/4 du is going to be dx. Okay, so then we would get 1/4 cosine of u du, which gives us 1/4 sine of u plus c, and that gives us 1/4 sine of 4x plus c. So after you do enough of these, you'll sort of see that the 4 is just going to be 1/4 out front. So some of you are probably there. So when you see this, you can just go right to this. You can say, okay, this is equal to 1/2 times x plus, and you see that 4, and you know you're going to need a 1/4 to take care of it. Okay, so some of you I know are there. If you're not, you just do a few more of these and you'll see, like when it's something like this, I'm just going to have to deal with that 4. It's going to end up being a 1/4. Okay, then from here we can distribute the 1/2 through there, and we'll get this is equal to 1/2 x plus 1/8 sine of 4x plus c. All right, so that is an example where we've got an even power of cosine, and even power of sine would work the same way with the other identity. And that takes care of the sine and cosines, which are the ones that you'll see the most, but I know you would be very sad if we didn't also talk about secants and tangents. We've got 3 cases for these. And these also work with cosecants and cotangents, although those are even less common. So you've got something like this. You've got an integral with some power of secant times some power of tangent. And there's 3 cases here. Okay, so case 1 is you have an even power of secant. So in the even power of secant, we're going to leave one of those factors of secant squared for the du. So we leave one of them of secant squared, and then we're going to go with this other trig identity. We're going to use this to express the remaining portion as powers of tangent. And then when we do that, we're going to let u be tangent and du would be secant squared. Okay, so that's case 1, even power of secant. Now case 2 is when you have an odd power of tangent. So when this happens, we're going to keep one factor of tangent for the du. Now the du is also going to need a secant, so this one's going to be a little different, but we're going to strip off a factor of tangent, or keep one factor of tangent, but we also need a factor of secant, because we're going to let u be secant, so du will be secant x tangent x, okay? And then we'll use this trig identity, just a different variation, where this one is solved for tangent squared, right? These are both just this are from the same identity, from the Pythagorean identity. Okay, so in this case, we'll use a different version of that identity to make that one work. And then this last one is sort of a catch-all for case 3, sort of a catch-all for cases that don't fit in case 1 and 2. This one, we're going to rewrite everything in the integrand strictly in terms of secant using this trig identity. And then this one's a little bit of work. So we're going to integrate by parts twice and solve algebraically for the desired integral. So that's sort of like, if you remember we had that problem from 7.1, I think we had a problem something like e to the t times cosine of 4t dt. It was something like that where we went through, we did integration by parts twice, and then this reappeared in the answer, so we solved it algebraically. So it's something like this. So sometimes that'll happen when you have an odd power of secant and an even power of tangent. It's sort of a lot of work when that happens. Okay, but let's take a look at one of these. Let's take a look at example 7. And we're going to do something similar to what we did before. I want to do this 2 different ways. Because this one, we've got an odd power of tangent and an even power of secant. So we could use case 1 or case 2 here. Right, so the first thing for this one, let's first just use the even power of secant. Okay, so use the even power of secant on this one. So with that, what we'll do is we'll rewrite it like this. We'll say, all right, this is equal to tangent cubed x times secant squared x times secant squared x dx, right? So we're going to use the even power of tangent. We're going to peel off 2 here. So this is the same thing, right? The secant to the 4th. But we're going to let this be the du. So then u will be tangent and du will be secant squared, which means we need to change this into tangent. Okay, so we can change this into tangent because we know that tangent squared x plus 1 equals secant squared x. So I'm going to use this. So I'm going to rewrite this as tangent cubed x times tangent squared x plus 1 times secant squared x dx. Then I'm just going to distribute this through. And we'll get tangent to the 5th x plus tangent cubed x times secant squared x dx. And once we're here, now we are ready to do a substitution. We can say, all right, let's let u equal tangent of x. Then du equals secant squared x dx. So we've got our du right here. So we can now substitute and we will get u to the 5th plus u cubed du, which of course is going to be 1/6 u to the 6th plus 1/4 u to the 4th plus c. And now we can substitute everything back in there. So we swap it all back and we will get 1/6 tangent to the 6x plus 1/4 tangent to the 4th x plus c. So this will be our answer. And then what I want to do also is do the same thing, but same problem, but now we're going to use the odd power of tangent and just compare the answers. All right, so here's the same problem. Tangent cubed x times secant to the 4th x dx. But this time we're going to use the odd power of tangent. Okay, so what we're going to do, peel off one of these, and then we're also going to have to peel off one of these because we need secant tangent. Okay, so for this one, we'll go, all right, I'm going to take off one of these tangents, so I have tangent squared x, take off one of these secant cubed x, then I'll have secant x, tangent x, dx. This time we want this to be the du, so the u is going to be secant, so I need to do something with this. We go back to the original expression. We usually, for the Pythagorean identity, I usually write it like this. Tangent squared plus 1 equals secant squared x. Okay, but this one, I'm going to need to write it in terms of secant. So if I solve this for tangent, I just have to subtract 1. So I'll get tangent squared x equals secant squared x minus 1, right? because I just started from here and just subtracted 1 from each side. So tangent squared x is secant squared x minus 1. So I can write secant squared x minus 1 times secant cubed x times secant x tangent x dx. Now we want to distribute this through here. Okay, so this would be equal to secant to the 5th x minus secant cubed x times secant x tangent x dx. Okay, and then we're ready to go right here. Okay, we've got our du, so our u is going to be secant. So we'll go u equals secant of x, du equals secant x tangent x dx. So then we can substitute this out and get u to the 5th minus u cubed du. This will be 1/6 u to the 6th minus 1/4 u to the 4th plus c, which is equal to 1/6 secant to the 6th x minus 1/4 secant to the 4th x plus c. So if you compare the last two formulas, the last two answers we got, they really don't look too much alike. We got secants instead of tangents. But if you happen to graph these, you'll get something very similar. You get they're basically the same graph, just with a vertical shift. So just remember that sometimes you're going to get an answer that maybe varies from the back of the book, because maybe the author did it this way and you did it this other way, so you get different answers, okay? So that's something that could happen. One other thing that we need to know about, just to make the homework a little easier. So there is a problem in the homework, and there is a trig identity we need to know about. So I just mentioned there's this trig identity. There's a few of them. So this is in the book. There's this little, like, this area that's formula number 2. So, and if you have the 8th edition of the textbook, it's page 484 in the 8th edition. The 9th edition, it's on page 498 in the 9th edition. And this will come up when you're working on problem number 43 in the homework. And it's just, it uses trig identities when the arguments to trig functions are not the same. So it'd be like if you're working with something where there's a secant, this is maybe a 2x and this is an x. So there's some trig identities we can use. So when you're working on number 45 in the homework, it's number 45 in the 9th edition. I think the 8th edition homework was number 43. So that right there, those trig identities and equation number 2 will make life a little easier. But let's just have you try one of these problems, something very similar to the homework, maybe even right out of the homework. So let's try this one. So this problem, cosine to the 6x sine cubed x dx, we want to integrate this one. So if you think about what we just looked at for working with sines and cosines, case 1 said you have an odd power of sine x or cosine x, and case 2 says both sine x and cosine x have even powers. So this is not case 2, right? They don't both have even powers. This is definitely case 1. So case 1 says strip off one factor of the odd term to be the du. Right, so we're going to strip one of these signs off of there. So this is going to end up being cosine to the 6x times sine squared x times sine of x dx. So sine of x is going to be the du, which means the u has to be cosine. So that means I need to make this in terms of cosines. I just want the sine to be here. All this we need cosine. So I'm going to swap out the sine squared. So this is going to be equal to cosine to the 6x. Now sine squared is 1 minus cosine squared x times sine of x dx. Right, so then from here we've got our du here, and then we've got what's going to be the u's over here. So let's go ahead and distribute the cosine to the 6x through here. And that would give us cosine to the 6x minus cosine to the 8x times sine of x dx. And at this point, we can do our substitution. We can say u equals cosine of x, du equals negative sine of x dx. So then negative du equals sine of x dx. So we could then say this is equal to u, well, we've got the negative, right? We've got a negative there, so we've got u to the 6 minus u to the 8 du. And I'm just going to distribute the negative through and rewrite this as u to the 8 minus u to the 6 du, just so I don't have to deal with the negative at the end. So we've got this, if this comes through, it's going to be make it a negative u to the 6, which you've got here. Make it a positive u to the 8, which you've got here. This way, I don't have to worry about distributing through at the end. Then we can integrate this, so we get 1/9 u to the 9th minus 1/7 u to the 7th plus c. Then resubstitute, we get 1/9 cosine to the 9th x minus 1/7 cosine to the 7th x plus c. And that should give you all you need to get started on 7.2. So go ahead and give it a shot, and you know what to do if you're into any trouble. Just let me know. Send me an email or ask me questions, and we can take care of your questions. So give it a try, and I will talk to you soon.